you that angular momentum is a conserved quantity, which means that if there's no external torque acting on the system, momentum is conserved. That's the phrase you need to know. So I'll say it again. If there's no external torque acting on your system, then momentum is conserved, or momentum stays the same. Momentum is the product of moment of inertia and angular velocity. And there can be lots of objects that are spinning in your system. But when we talk about conservation, there are two things that you have to understand. Conservation requires that the net torque be equal to 0. That's what the math looks like. The net torque. There has to be no unbalanced torque acting on your system. If that's true, then when you add up all of the momentums of all the objects in your system, when you add them all up, no matter how many there are, they'll equal some constant. And the sum won't change. That's what conservation of momentum means. The most important difference, the thing that is very different between linear momentum and angular momentum, is that it's possible for an object's moment of inertia to change. That's pretty messy, but I'm trying to write these things down. I think you really need to understand or really need to know. So an object's moment of inertia can change. It can become bigger or smaller. When that happens, the object's rate of spin will change. Meaning an object can make its momentum smaller and it'll spin faster. And the reverse is true too. The object can make its momentum bigger and then it's going to spin slower. And although we laughed a little bit about it, we watched a couple of videos. The kids all trying to climb to the center of the merry-go-round makes the moment of inertia smaller, so the spin rate increases. The ice skater who puts her arms outward slows down, then when she pulls them in, speeds up. Now, there is something over the top of this that I want to put out there. It's going to be on your test, and you probably should be aware of it. We're going to look at the math of it, but before we look at the math of it, I want to put it in a big box here. This doesn't mean energy is conserved. The only way to know if energy is conserved is to check. And that's the first thing we're going to do. We're going to practice one all the way through where we check at the end to see if energy is conserved. Now, I'm going to hit. So in this problem, which we have two people on it, they're at the outside edge. It's spinning one revolution every 10 seconds. The people are going to walk from the outside edge to the center. And when they do so, they're going to decrease the moment of inertia of the ride, so we expect the ride to get faster. That's what our expectation is going to be. So there's a number of ways to do this. I'm going to do this piecewise, which means I'm going to take one piece of the problem at a time and look at it a little bit at a time. So my first piece is to remember that angular momentum is the moment of inertia times the speed. That's where I want to start. So what I really have going on over here is the moment of inertia before the people walk to the center times the speed before they walk to the center is going to equal the moment of inertia after they're at the center times the new speed when they're at the center. Since the whole thing is like one object, we're going to see their speed be related directly to how fast the ride is going. So, to make this a little bit more straightforward, I'm going to go off to the side here, and we're going to calculate the moment of inertia separately. Because there's three things that contribute to the moment of inertia. There's the moment of inertia of the merry-go-round, there's the moment of inertia of person 1, and there's a moment of inertia of person 2. So there's three things that contribute to the moment of inertia. Although you don't have to memorize it, most of you at this point probably remember what the moment of inertia of a disk is. So a disk has a moment of inertia of 1/2 mr squared. Each person also has a moment of inertia. They are a point mass, and they will be mr squared for person 1 and mr squared for person 2. Bless you. So now I'm just going to drop the numbers in because we have some numbers to work with here. So starting with the disk, I'll have 1/2 times 150 times 2 squared plus person 1, which is 60 times 2 squared, plus the other person, which is 60 times 2 squared. Now, this is just using your calculator, and I know you guys can do this, so I'll give you a second. I think it's 780 though. Is it 780? All right. You guys make sure. It's going to go right there. So, units, 780 kilograms meters squared. All right, now I need the angular speed. So I got to find that piece, the angular speed. So to find the angular speed, let's ignore this for a few minutes. I'm going to get rid of the moment of inertia calculation because I don't have that much space to work with. Angular speed is in revolutions per second. And here's a tidy little trick you might want to know. If you look carefully at this relationship that we got sitting up here, this one right here, do you notice that I have moment of inertia times speed equals moment of inertia times speed? If I leave the speed in revolutions per second, my answer is just going to be in revolutions per second. So although I've always told you that it's best to convert to radians per second, I could go ahead and do the work here without converting and it would be okay, as long as I know that my answer is going to be in revolutions per second. So if we can follow that logic, I don't have to do any converting. I can just go ahead and put 1/10 here and know that my answer is going to be in revolutions per second. Now, if they ask for an answer in radians per second, you're going to have to do something else. But for right now, I'm just going to leave this as 1/10 revolutions per second. Now again, the proper way would be to convert this to radians per second, which means multiplying by 2 pi. But I think we're able to kind of come to grips with this. All right, we're getting close. We want to find the speed after the people walk to the center, which means we now need the moment of inertia afterwards. So, to get the moment of inertia afterwards, when the people are at the center, they'll be here. What's their distance to the axis of rotation now? 0. So my moment of inertia changes drastically because my moment of inertia is going to be the moment of inertia of the disk. That's still there. But now each person contributes nothing to the moment of inertia because they're standing on the middle. Now I know both people can't actually be standing on the middle, but it is February and I'm sure love is in the air. Maybe they're embracing in some lover's embrace and have become one with the, well, I can't even spit all that out without vomiting in my mouth a little bit. So let's just say that that's 0 because it's easier for the math. There, that's romantic. So that's 300, right? So I'm going to put my 300 right there, 300 kilograms meters squared, leaving me with omega A on the outside. Because there's not much left to do. I think all of you can kind of see where this goes from here. I need to solve for omega on the outside. I got 780 divided by 10. That's going to be 78. So the left side will be 78. The right side is 300 times omega. So omega is going to be 78 divided by 300. And the units here will be revolutions per second. It's hard to compare this with the 1 revolution every 10 seconds. It's hard to know if this is faster or slower. So I want to show you something else here. First, though, can you get this to a decimal for me? That would be nice. 0.26? 0.26 revolutions per second. That equals omega. Now, the original omega was 1 revolution every 10 seconds. So we start out at 0.1 revolutions per second and increased 2.5 times faster. So that's pretty significant. It's going a lot faster now than it was. Could you see me asking you how long it takes to go around now? Could you see me asking that question? I want you to understand that that's a fair question to ask you what the period is. And if the first one was 1 revolution every 10 seconds, do you realize that the inverse of that is 10 seconds per revolution? Do you guys understand what an inverse is? So if I take the inverse of this, which means 1 divided by 0.26, this would be seconds per revolution. Can you tell me how many seconds it is per revolution? 3.85 seconds per revolution. So originally when we watched them go by, it took them 10 seconds. So they left, counted to 10, they came back. Now, if we're watching them, they're spinning in the center, but they spin once every 3.85 seconds. Okay? You guys see how we got that number? So I'm going to say it again, and you should put this in your notes. That the period of rotation is the inverse of the angular speed when it's in revolutions per second. The period of rotation is the inverse of the angular speed when it's in revolutions per second. Okay. Typically, if this was the end of class, I would say you could do this on your own because it's just calculating energy, but I have shown on a test that that doesn't always work out. So what I want from you now is something that we can all do together, but I'm going to provide a little bit of guidance. I want to compare the energy before and after. We're going to compare the energy both before and after. The kind of energy we're talking about here is kinetic energy because things rotating. That's 1/2 I omega squared. Big difference here. Omega has to be in radians per second. Has to be. That produces an answer in joules. So before, we didn't have to be so critical about it. Here, have to be critical. You have to be in radians per second. We have 2 speeds to worry about too. The speed before was 0.1 revolutions per second. This will have to be converted to radians per second to be used. And the speed after, we found to be, help me out, 0.38? 0.385? I don't remember. 0.26, so I clearly don't remember anything. That's right, 0.26. And that's going to be revolutions per second. So we have to convert these to radians. Again, I use unit multipliers. I want to cancel out revolutions and be left with radians. So I put revolutions on the bottom, radians on the top. There are 2 pi radians for every 1 revolution. So I am multiplying this by 2 pi. Let's see, 2 pi is 6.28. So the angular speed before is going to be 0.63 radians per second. I did the easy one. You guys have to do the hard one, because I can multiply by 0.1 in my head, but I can't do this whole hard one over here. So you guys figure out the angular speed after in radians per second, and I'll take a coffee. All right, who got the before number? Can somebody raise their hand? Yes, ma'am.
154.8.
Everybody else get 154.8? Yeah. Sounds good. I'm gonna go 155. Okay. 155. J for joules. Let's not forget our units. All right. Somebody else tell me the after one. 399. Anybody else get 399? Yep. All right. I'm gonna go 400 joules. Now you clearly see that there's an increase in energy here. Do you guys see that? There's no trick. This is not because the people disappeared when they got to the center and we used a radius of 0. There's an increase in energy because as they walked forward, they did work on the merry-go-round. You need this in your notes. You need this concept in your notes. That in these systems, energy is not going to be conserved. It's a momentum problem. Work was done by the people when they were pushing against the ride to walk to the center. They did work on the ride. When I ask this question in class, on your test, to compare the energy, and I ask, where did the missing energy come from? Because the energy increases here. The way to answer that is to understand the concept of work. Something did work on the ride if the energy increased. Since nothing touched the ride but the people, they had to be the ones that did the work on the ride. In fact, the most often asked question will be by what percentage did the energy go up? So I'll be asking you to do things like take the after and divide by the before and find this ratio. That is very common on the AP exams to ask about the ratios to see how things increased by looking at a percent difference or a ratio. In this case, the energy is over 2.5 times bigger. Or close to 2.5 times bigger. That's a lot of extra energy that came from them walking to the center. Now look, you guys watched the video. Did you see those kids straining to try and get to the center? It was hard to do, and the faster it went, the harder it was. They had to apply a lot of force to the ride to get to the center. That's why work is done. They are tired when they make it to the center. They're doing work. This ice skater speeds up. She has to do work on her arms to pull them in. And although that increases their speed, it does also increase her energy. And the reason it works mathematically is because the angular speed is squared. This, if you're ever asked why, it's because the angular speed is more important in energy than it is in momentum. So the reason the math works out is because we square that velocity.